Hello everyone and welcome back. So in the last video, I showed you how to approximate the solution to a differential equation using what's called Euler's method, or the forward Euler method. Now this is a numerical procedure that can allow you to take current approximations of your solution and push them forward to get new approximations to your solution further into the values of t beyond your initial condition. Now, a lot of what that relies on is the fact that you actually have a solution to your differential equation, right? There's something behind this that we can actually approximate. Now, what I also emphasized is that we can find out exactly when we have a unique solution. In fact, we talked about it quite thoroughly in this lecture series. We talked about existence and uniqueness theorems. And if you remember, the one that we really focused on, or the one that was most interesting, was the one for nonlinear first-order differential equations, where we had the initial value problem that looked like this. Now, what I did is I immediately made things a little simpler. You're going to note that right off the bat. I set t naught equal to 0, and I set y naught equal to 0. This is something that can always be done without any loss of generality in math. I just want to make my life a little easier, and you'll see why, hopefully, as I progress through the lecture. It's just one less thing to write as we go through. But nonetheless, I told you that this thing has a unique solution as long as f is continuous on a box or a rectangle that contains, in my case, the origin, 0, 0, and the partial derivative with respect to y of f is also continuous on the same rectangle. Now, did you ever sort of, did it ever occur to anybody who watched this to ask yourself why, right? How do you prove that thing? Well, the proof is a very well-established technique in mathematics. It's known as sometimes Picard iteration, after the mathematician who first did this, Picard, or sometimes we call it just the method of successive approximations. Now, I'm not going to do the actual proof of this thing, but what I want to do is I want to show you how it actually is done, so how you set up the proof of this thing without actually doing it. And then I want to exemplify how we can use this proof to actually find solutions to differential equations. So bear with me for a moment here, but let's remember that we have, let's assume that we've got a unique solution. So a unique solution, y equal to phi of t. Okay, so since this is a unique solution, I know that phi prime is equal to f of t comma phi of t for every value of t where that solution exists, right? In some region of the origin. Okay, then, so let's actually write this down. This implies that phi prime of t is equal to f of t comma phi of t. Okay, so assuming phi is known, I could just straight integrate that. And that means that if I integrate this from 0 to t, I get phi of t minus phi of 0. Now, because I assume this thing goes through 0, I don't have anything else here from the fundamental theorem of calculus. That's why I did it. It's one less thing for me to write. But this is now equal to the integral from 0 to t of f of s comma phi of s. So I'm using s as my integration constant, ds. And also, we just remind ourselves, right, this is my initial condition. Phi of 0 is equal to 0. So just in case you're wondering where that piece went. Okay, so you're sort of thinking to yourself, Jason, I'm not really sure why you think that was going to help me. And I don't expect you to see that right off the bat. But it's actually in this form right here. This is called the integral form. Sometimes it's a weak formulation of this, this differential equation because there's no more derivative. We turn the derivative into an integral. It's this thing that people do all the work with. Actually, you can show that solutions exist to this thing. And the way you do this is through what's called an iteration procedure. So you can actually prove that if you take this integral, 0 to t, and you put in some guess, so let's call it phi n of s. So just say you think the solution is going to be some function, say cos of t. I don't know. Maybe there's something that makes you think that, right? That can be your guess. And what you can do is you can put it into f, and you can do this integral, right? I know what f is, and so therefore, this is an integral that can be done, at least in principle. Then what you get is a new function. I'm going to call it phi n plus 1. Okay, so you give me a function. I call it phi n. I do the integral. I'm integrating from 0 to t, so I get a function of t again. And I get a new function of t. I call it phi n plus 1, the update, right? So you start with an initial guess, say phi 0. So this is going to hold for n equal to 0, 1, 2, all the way out. So you give me your initial guess. Say that's your cosine function. I do up the integral. I get a new updated guess. Call it phi 1. Then you take phi 1 and you put it back in here. You do the integral. You get a new guess, phi 2. You take phi 2, you put it in, you get a new integral, you get phi 3. And you can do this ad infinitum. And this is exactly the same procedure, the same idea that is being done behind Euler's method as well, right? You take t naught, y naught, you use it to push forward to get t1, y1. Then you use that to push forward to get t2, y2, then t3, y3, right? So you're using your current step to get the next step. Same thing here, the only difference is instead of going through points, I'm going through functions. Now the way that the proof of this uniqueness exists is that we can actually prove using mathematics, like rigorous analysis, that this procedure is always going to settle down. It will always converge no matter what solution you start with, as long as it's continuous. So, and you can even go further, and you can show that it always converges to exactly the same solution. Right? So that's existence. It converges, right? Because if something goes into this and comes out of it, if it's a fixed point here, then it's a solution to my differential equation just by these two lines. But also, if you start with cosine and I start with sine and we do this iterative procedure, then we're both going to get to exactly the same solution. Maybe it was e to the t or something like that, right? We're both going to get the same answer. I'm not going to do the actual proof here because that requires a little bit, a level of mathematics that's sort of beyond the scope of this course. But here's what I'm going to do. I'm going to show you how you do this in practice. We're going to do this with an example. So let's take a look. Okay, let's say y prime is equal to 2t times 1 plus y. And I'm going to use, again, y of 0 is equal to 0. So I'm going to match up my initial conditions. 2t times 1 plus y, linear equation. If you want to, you can use an integrating factor here. It's also separable. You could use a separation of variables. We'll find the solution at the end here. But before we do that, let's actually do the first few levels of this iterative procedure. Now, let's keep one thing in mind. I told you no matter what you start with, you're always going to converge to the solution, the unique solution, right? This thing is linear. It satisfies all of the conditions to guarantee there exists a unique solution. So I don't really have to worry about that. What I have to worry about is where I want to start. Now, maybe you have a different opinion on this, but I think there is one function in particular that is the easiest continuous function to start with. And that is the constant function 0. So that's what I'm going to do. I'm going to start my iterative procedure with 0. I know that no matter what I start with, I get to the unique fixed point. So start with the easiest thing, right? I don't like doing hard integrals. So here, phi of 0 of t is equal to 0. Okay, so that's my first guess. Maybe I'm feeling a little lazy today. I said, yeah, solution is probably 0. Well, you're gonna put this in. You're gonna get your update, phi 1 of t. And you're gonna say, actually, Jason, no, because you don't get 0 back out of this thing. if you perform this integral, phi 0 of s ds, so this is f of s comma phi of s, or phi 0 of s. It's just this thing right here being integrated. This is 0, which means that I'm just integrating 2s from 0 to t. This is just t squared. Okay, so here's what happened. I guessed it was 0. And when I put 0 into this iterative procedure, I got out t squared. So I got a better update. I got, actually, it's closer to t squared. Okay, well then let's get a closer approximation. Let's go again. Let's use phi 2 of t. Phi 2 of t is obtained through, again, this integral, phi 1 of s ds. Now, phi 1 of s, let's go ahead and just replace that right off the bat. That's just s squared. So now I get 1 plus s squared inside there. These are polynomials, right? I can do these integrals all day long. So what do I get now? I'm going to get t squared plus t to the 4 over 2. So take a look at what my solution is doing, right? What this iteration is doing. Started with a terrible guess 0. Said, it's actually, t squared is actually a better one. You should have started with that, right? Then I put in t squared and said, actually, t squared plus t to the 4 over 2 is actually much better. T squared, t squared. What does it look like is happening? It looks like I'm kind of building a series, right? So let's try again. Let's keep going. Let's go with phi 3 of t. Again, integral from 0 to t, 2s, 1 plus phi 2. Now let me just put it right in. S squared plus s to the 4 over 2 ds. So 1 plus s squared, 1 plus s squared. I'm going to get that piece out of this again. And I get t squared plus t to the 4 over 2 plus t to the 6 over, I'm going to write it as 2 times 3, okay? And you probably know why I'm going to write it as 2 times 3, because I want to be able to recognize a pattern as I go through this thing. But look at t squared plus a correction, t squared and its correction plus another correction. What you can do here is you can identify a pattern. So you can say, in general, so if you want to, you could prove this with mathematical induction, right? And you can say that the general form, so if you do this up to any iterate little n, this thing is actually going to give you t squared plus t to the 4 over 2 plus t to the 6 over 3 factorial. So 2 times 3, there's no 1 in there, it doesn't matter. Similarly, technically, 2 is equal to 2 factorial. And then if you just look at the general term here, it's t to the 2n over n factorial. So again, if you want to prove this is the case, use induction. That's fine. We're not going to bother with that yet. But remember I told you that this is the general term phi n. We know that this thing converges as n goes to infinity. So the question is, what should we expect this thing converges to? Well, so if we say letting n go to infinity, this implies that the limit, the limit is n goes to infinity of phi n of t. So I'm leaving a lot of mathematical details in the background here. What I'm showing you is sort of how this actually works in practice. Well, I'm going to call this phi of t. This is the solution. And this is given as an infinite series. This is from k equal to 1 to infinity of t to the 2k over k factorial. Now I've got the solution written as an infinite series, right? This is the solution. This is the unique solution. And see how we did it, right? This is very exciting to me. Again, this is an iterative procedure, just like Euler's method from the last video, that just uses information from the previous step to get a better update. What happened here? We built down a series. In general, I get this phi n up to a power of 2 to the n. Then if I put this into my iterative procedure, I get another series that goes up to 2 to the n plus 2, the next power in this sequence. So what does this mean? It means I can do it on a computer again. I love computers, right? Because they do all the hard work for us. So I could, again, set up a for loop on, say, Mathematica or MATLAB or something like that, that symbolically does the integration for me, takes the integrand from the previous one, which would be, say, my phi sub n, puts it into this thing, does the integral again, gives you the update of the solution. The more terms I have in this sum, the better an approximation, right? You probably, hopefully, have learned infinite series before you started looking at this video lecture series. And so you have a pretty good understanding of what's going on here. The more terms you take in this, the better the approximation, right? This is a power series. Actually, in fact, we can figure out what that power series is, right? And you can figure out what that power series is in 2 ways. First of all, use your old school calculus knowledge and just sum that thing up, right? It might take a little bit of work. You might have to really dig into the recesses of your mind to remember how to do that. But you can do it. Alternatively, you could just solve the differential equation. Sorry, here it is. Why? Because there's only one solution. If you sum that thing up, or if you solve this thing, you get the same solution. So, in fact, we actually know that phi to the t, or phi of t, sorry, is e to the t squared minus 1. That's it. Nothing fun. Or nothing too exciting. And you can see the t squared coming from this t to the 2k that we're counting along here. Okay, so I keep using this idea that my solution is exact. The question is, how do I actually know that this solution is exact, right? Can I check? I mean, I've got a concrete example that I'm sort of wrapping myself around here. Maybe I can actually just check in this context and give us some idea of what's happening. Well, let's do it. So let's do this. So let's say unique, question mark. Let's suppose phi and psi are both solutions, okay? Are both solutions. So what does it mean to be a solution to a differential equation? Go all the way back to the second lecture video in this series, right? If you want the proper definition. But really it just means this, right? It satisfies this thing, which means it satisfies this thing, right? It's a fixed point of this iterative procedure. Fixed point means I put it in, I get it right back out. That's what this is saying. So if I've got 2 fixed points, that tells me this. This tells me phi of t is equal to this integral, f of s comma phi of s ds, and psi of t is equal to the integral from 0 to t of f of s psi of s ds. This is the sort of general piece. In this case, my f is known, so let's go ahead and do this. So what I could actually say is that phi of t minus psi of t, so if I subtract these 2 things using this integral, well, I can move them both inside the integral. And since f is equal to 2t times 1 plus y, then I get 2t times 1 plus phi and 2t times 1 plus psi. And this leaves me with, it becomes an s inside of the integrand. And this should be phi of s minus psi of s. ds. Okay, so again, I've got a little fixed point thing here. I'm saying that the difference between these two functions is equal to this integral that again involves the difference between these two functions. Okay, that's lovely. Now, here's what I want to do. I want to slap an absolute value around this thing. So let's take an absolute value here. That will actually put an absolute value around all of this integral. Okay? And the reason I'm going to take an absolute value is because I know that if I put anything that's equal to 0 into an absolute value, it gives me 0 back. But also, I know that the absolute value of something equal to 0 implies that my original thing was 0 as well. So basically what I want to show is this is equal to 0, that phi and psi have to be the same thing, because that's going to give me uniqueness in my solution. Well, I can take an inequality here. The inequality is going to bring my absolute values inside of my integral. So now I've got the integral on the outside. So it's a very common inequality that comes up in real analysis. You can actually see my real analysis lectures for where you can prove this. And now you get 2 times s, and then phi of s minus psi of s ds. Okay. Did that help us? Not much, but let's take a look. Here's my difference in absolute value. Here's my difference in absolute value. They're both in here together. And so what I can do is, let's say, let's suppose that we're going to look from for t between 0 and a over 2, where a is going to be any number, okay? But I just want some finite number that we go up to. The reason I have a over 2 is because of this 2s here. So what this actually tells me is that phi of t minus psi of t is less than or equal to, now, s is bounded by t is bounded by a over 2, so 2s is just bounded by a. Okay, that's the only reason I wanted to do that. I just want to put some number out front. It's a real number. Doesn't matter what it is. So don't be too intimidated, especially if you haven't done much real analysis looking at this. But it is important to sort of see the inner mechanics of this. Okay, now here's what I want to do. So I'm kind of use a different color at each step to really sort of emphasize this. Let's say set, I'm going to call this thing big U of t. And this is going to be this entire right-hand side. The integral from 0 to t of phi of s minus psi of s ds. Well, what do we know about this thing? First of all, u of 0. So if I integrate from 0 up to 0, well, that's a sort of null integral, right? There's nothing to integrate. You're integrating from 0 to 0. This is one of the rules of integration. If you integrate from the same point back to itself, you're integrating nothing, right? Think about the formulation in terms of area underneath the curve and in terms of Riemann sums, right? You just have a rectangle with no width. Okay, that's an easy one. Also, this is an absolute value in here. Absolute values are non-negative by definition. So if you are integrating a function that's non-negative, you again get a function that's non-negative. So you also get that u of t is positive. Okay, I mean, I'm giving you things, but you might still be wondering, what was the point, right? What is it that I'm supposed to see here? Well, this formula right here, this whole thing right in front of me, that right there is the derivative of u, right? So this is a derivative of an integral. So if I take u prime, I can use the Leibniz differentiation rule for integrals. You might have to look this one up. You might have to refresh yourself. Essentially, it's just the fundamental theorem of calculus. But that will give me, so this piece right here is u prime. So u prime of t. This is less than or equal to a times u. Okay, which, let me rearrange this. Just like this. Now, what was the point of me doing this? Well, here's something interesting. That looks like something I would use an integrating factor on, right? So everything is starting to snowball, right? Where everything that we might have used, a few lectures ago and felt like we just used it once and discarded of it, well, it's coming back. So in fact, this could be written as e to the minus at u of t and d dt, because this is an integrating factor. And again, the inequality here is preserved. And that just comes from the fact that I've got this non-negativity of my function u. Okay, so I hope I don't make anybody too seasick by doing this, but I don't have much more to write, so I'm going to put it up in this corner here. I can integrate that, right? Inequalities are preserved by integrals, and that again comes from the fact that what I'm integrating on the inside here is a positive function. U is positive, exponentials are positive, so this actually gives me e to the minus at times u of t is less than or equal to 0. Okay. This thing is always greater than or equal to 0. Now, this multiplication is negative. U of t is less than or equal to 0. We got a problem, right? Because right here, I said that u of t is positive, or non-negative. Right here, I'm saying u of t is non-positive. The only way both of these things can be true is if u is equal to 0. And this is true regardless of what the value of t is. Okay, so now, if this is equal to 0, this tells me that because I have u of t is equal to this integral, the only way this integral can be 0, because we're integrating something non-negative, is if phi of t is equal to psi of t for all t greater than or equal to 0. Okay, so we went pretty far down the rabbit hole there. What did we actually do? Okay, let's go all the way back to the beginning of the example, and let's walk ourselves through this sort of mess of a board here. What happened? I gave you an ordinary differential equation and an initial condition. So that means that I gave you an initial value problem. And what I did is I said, well, maybe the solution is equal to 0. It's not, right? But it doesn't matter, because I know that if I perform this Picard iteration, I can get better and better approximations at the solution. So I took my junky initial condition, I put it into this iterative procedure, I got down a new guess at the solution, phi 1 of t, which is t squared. Much better approximation than 0. Then you said, well, Jason, I can do better. I'm going to take your t squared, I'm going to put it into the procedure again. I'm going to get a better approximation, I call it phi 2. Right? So I took my old t squared and it gave me a little more. Then we did it again. We said, okay, take this thing, put it in, give me a phi 3. I got my old solution, my old approximation plus a little more. A little error correcting at every single step. I'm getting a little bit better. And then I said, wait, I know what's going on. This seems to be what's happening here, right? And I could even prove it with induction if I wanted to. Then I said, well, Jason told me that this iterative procedure always converges. So what happens as I let n go to infinity? Well, if I let n go to infinity, I go to a solution of the differential equation, and that solution is given in terms of this sum. Then I know what that sum is equal to. I can use sort of results from calculus, or I could just solve the differential equation. There it is, right there. So then I started questioning myself. I said, this seems too easy. Is it possible that if Jason and I did this, and if I used a different initial guess, we would get different answers? Well, then we started saying, imagine if there was two different solutions. Then we walked ourselves through this sort of logical chain of arguments here, and we figured out that if there was two answers, two solutions, the only way things would work is if they were exactly the same. That is, there's only one solution. It's unique. That's what we're getting with Picard iteration. That's why if you look at the statement of this existence and uniqueness theorem associated to this ordinary differential equation right here, this initial value problem, I said not only does there exist, right, so I had this symbol in there, I said there exists a unique, that's what the exclamation mark is, there exists a unique solution. There exists a unique. So all I did here today, I did not prove that theorem. What I did is I walked you through how you can practically use the proof of the theorem. And in particular, the practical aspect of it is right here. I can get better and better approximations of my solution in the same way that I can build a power series to better and better approximate functions that I might be interested in. Things like Taylor series, right? We think of e to the t is just the sum of t to the n over n factorial. Same basic premise here. We're just applying it to differential equations.